Hello everyone, myself Shamli, Assistant Professor at SVC. I've always been fascinated by how machines can be taught to see and interpret the world around them, much like human do. Today we are going dive into the topic, the exciting and rapidly evolving field called a computer vision, a branch of artificial intelligence that enables the computers to understand, analyze, and process the images and videos. So, without further ado, let's go into the topics. KLT algorithm steps. The KLT algorithm steps, which tracks the feature point across the consecutive video frames using the optical flow. The process can be summarized as follows. So here we can go with the feature directions. It identifies the good features to track in the first frame. Typically, the corners or the points with the strong intensity changes in both x and y. The directions are chosen. So the popular methods like Chai-Thompson's corners detectors or Harris corners directions. So we can go for the window selections. So for each directed features, they are selected a small neighborhood windows around it. That is, example 5 cross 5 or 9 cross 9 pixel. Assuming all pixels in these windows moves with the same displacement. It compute the image gradients, calculate the spatial intensity gradients, that is I of x comma I of y in the windows. It computes the temporal gradient, that is I of t, as a difference in intensity between the consecutive frames. Here it forms optical flow equations where it applies the optical flow constraint equations for all pixels in the windows. That is I of x into u plus I of y into v plus I of t is equal to 0. This creates a system of linear equation for the velocity components u and y. To solve for motion vector is that you have to use a least square to solve the system and estimate the displacement u comma y of the featured within the windows. So we are going to update the feature position. Here we are going to move the feature points to its new positions in the next frame based on the estimated velocity. Here the validations and tracking is that check if the feature is still valid, that is not lost due to the oscillations, the motion blur or leaving the frames. It keeps the valid features and optionally detect new ones to maintain the robust tracking. We have to repeat for the subsequent frames. So it performs the same process for each new frame, tracking all valid features across the video sequences. So the optional enhancement I can say is a pyramidal KLT, where for a large motions a multi-scales or the pyramidal approaches is used. The optical flow is computed at core scales first, then defined at finer scales. This allows the tracking features with a larger displacement between the frames to go on. So as we discussed before, the first steps of the KLT algorithm steps is feature directions. After that, we have to go for the initialized tracking. For each selected features, the initialize is coordinates, that is x of 0 comma y of 0 in a frame 0. So the third steps here is to compute the optimal flow. For each features, the compute motions vector, that is u comma v, using the Lucas-Kennett optical flow. The first one is that we have to extract a small window, that is a patch, around the feature. The second one is a compute the spatial gradients I of x comma I of y and temporal gradient I of t, which solves the least squares problems, that is u comma v, the overall t is equal to at A, that is transform A transform into A, overall minus 1, the A transform into B. So here A is a matrix of a spatial gradients in the window, and B is a negative temporal gradient vector. And the step 4 is that update the feature positions. So it moves the features to its new position in the next frames. So x of new is comma y of new is equal to x of old plus u comma y of old plus v. And the step 5 here is a validations. It checks if the feature is still trackable, rejects the features with a low high eigenvalues like a poor textures, and discards the points with very large motions or the outside frame boundaries. And the 6 steps involved is a pyramidal tracking, that is optional for large motions. So it constructs image pyramids like a coarse to fine, so which tracks the features at a coarse levels, then refine the flow at a final level, ensures a robustness to a large displacement. So in the step 7 it involves like a repeat, like for every subsequent frames compute the optimal flow for a current feature positions, which update the positions, validate the tracked point, like build a trackable of features across these videos. And the last steps is a step 8, which is the output stage. Here a set of tracked features with trajectories over the times can be used for motion analysis and object tracking, or even a video stabilizations here. So in this Lucas Kennard's that is KLTs, we have seen about what is KLT, that is a Kennard Lucas Tomsey features tracker, and also about the extensions of this KLT to the optimal flow, and tracks a good features points across the frames. We also see about assumes a small motions and brightness constancy, how it uses the image gradient to estimate the motions. Even a corner features prefer for stability, and Stormzy and Kennard improves the feature selections too, which computes the displacement using a least squares. So these are some of the key points over that, and the pyramid levels handle a large displacement first thing, and it's also iterative refinement improves the accuracy with features lost or when accumulated also. So here the robust for the short-term tracking, we have to mention that, and widely used in OpenCV implementations of Python libraries, as well as it works in real-world applications we have said, and feature redirections maintains continuously. So here the motions vectors used for object tracking, yes of course, and it's assume the rigid transformations sensitive to illumination changes. So it's useful in a human pose estimations as well as a foundation for modern features based trackers. So this one all is about the overview of this topic. We can move on to the next topic. Spatio-temporal analysis. In a computer vision, understanding a motion is not just about observing where objects are at a single moment. It also involves analyzing how they move over a time. This is the essence of a spatio-temporal analysis, the study of patterns and changes in both space, that is a spatial domain, and time, that is a temporal domain. By combining the spatial and temporal informations, we can extract a richer insight about dynamic scenes like moving objects and human activities. Here, the key idea is that the spatial domains captures informations about the appearances and structures of object in a single frame, like shapes, edges, and textures. The temporal domains captures how these objects change or move across the consecutive frames, like speed, directions, or deformations. The spatio-temporal analysis fuses these two dimensions, allowing us to detect and recognize the complex motions patterns. Some of the application is the human activity recognitions. Here it detects the gestures, walking, running, or abnormal behavior by analyzing the motion over the time. Your video surveillance is that tracking the objects and understanding interactions between the multiple moving entities. Here the sports analysis come into the pictures where we are going to studying the player movement, ball trajectories and the game pattern. In healthcare, monitoring patients' movements during rehabilitations or detecting the falls in a elderly care. In robotics, we can say it is used for understanding the dynamic environments for navigations and interactions. So there are many techniques in a spatio-temporal analysis. In first one is a spatio-temporal filtering. It detects the moving edges or motion patterns by combining the spatial and the temporal gradient. The 3D convolutions uses a 3D filters across both spatial and temporal dimensions to extract the motion feature. Next one is a trajectorial analysis. It tracks objects over the time to understand the movement, paths and behavior. Here, the optical flow based methods computes the pixels wise motions and analyzes the patterns across the frames. Some of the advantages I can say, it provides richer motions informations than analyzing the spatial or the temporal data separately. It enables detections of subtle and complex patterns like interactions or repeated actions. It forms the foundations for a higher level task like behavior recognition, gesture detections, and video summarizations. To sum up, like its spatio-temporal analysis bridges the gap between a static image processing and dynamic scenes understanding by examining what changes, where, and how over the times. It allows machines to interpret motions in a meaningful way, enable applications in surveillance, human computer interactions, robotics, and healthcare as well as. So, for given overview of the spatial temporal analysis, spatial temporal analysis is a study of patterns and movement in a data that vary both in a space and a time in a computer vision. It helps in understanding motions, activity, and dynamic events in a video sequences rather than static images. Think of it like analyzing how things changes and moves over the times in addition to the spatial layout. In the conceptual understanding, we have to deal with the structures, shapes, and arrangements of an object in a single frames. Here, the temporal domains. These are all about a spatial domain. When it comes to the temporal domain, it deals with the changes between the frames over the time. That is a motion, appearance, or disappearance of objects. The spatio-temporal domain combinedly both allowing the system to track the motion patterns, detect activities, or recognize the behaviors. So, example I can say, it observing a person's waving the hands, the spatial, the hand shapes, and the position in each frames. The temporal here is a sequence of movements of the hand over the time. The next one is a spatio-temporal. Here, the overall waving patterns includes the speed, directions, and the frequency. So here, the key technique is a spatial temporal filtering, which is apply filters to detect the motions pattern in both space as well as in time. Examples: 3D Gaussian filters Gabor filters for motion detectors. Next one is optimal flow based methods, which computes per pixel motion vectors across the frames. So next one, it helps to capture local motions patterns and trajectories. So here the trajectories analysis is to track the moving objects or the features over the times. It used the feature trackers, that is example KLT, to build the trajectories. So here the dynamic texture modeling, which treats a moving region like a water, smoke, or a crowd as a spatio-temporal textures, which analyzes the pattern statistically over the space as well as the time. So here the STIP, the spatio-temporal interest points, detect the points in these videos where motions and a spatial structure change significantly, useful for action recognitions and event detections. So here the application I can say is that human activity recognitions to detect walking, running, jumping, and even waving the hands, etc. So here the video surveillance is identifying the abnormal behavior or suspicious activities. The gesture recognitions for HCI, human computer interactions, or even AR VR applications, augmented reality. So here the traffic analyzers, which tracks the vehicles, congestion patterns, and pedestrians flow. You can talk about the healthcare monitoring to analyze the patient's movements for a fall detections or any physical therapies. What are the advantage we can say is to captures both appearance and the motions informations, useful for complex dynamic scenes where static analysis fails. It supports higher level reasoning like action recognitions or behavior analysis. So what are the challenges I can say? It is high computational cost for a dense motion or a large video sequences. So it is sensitive to oscillations, lightning changes, as well as noise. So it requires efficient algorithms for real-time applications. The key insight I can give for this topic is that the spatiotemporal analysis is a bridge between detecting motions and understanding the activities. It goes beyond what moves to how and why it moves in a sense. So that's all about this topic. Let's move to the next topic. The next topic is a dynamic stereo. A dynamic stereo is an extension of a traditional stereo visions that deals with the 3D depth estimation in a dynamic or a moving scenes, while standard or like a stereo visions calculates depth from a two images of a static scenes. The dynamic stereo focuses on scenarios where both the camera and objects in our scenes may be moving. So this makes it essential for real-time applications like robotics, autonomous vehicles, and augmented reality and motion analysis in our videos. So here the stereo vision's basic key concept is a traditional stereo visions which uses the two cameras, left as well as right, to capture the same scenes from slightly different viewpoint. By matching the corresponding points in the two images, the disparity, the differences in position is calculated. The depth is then estimated using the triangulation, that is Z is equal to F into B by D, where Z is equal to the depth of the point and F is equal to the focal length of the camera, and B here is a baseline distance between the cameras, and D is a disparity. So the dynamic stereo challenges are it is moving objects can cause matches, ambiguities, since corresponding points may shift between the frames. So the camera motions adds another layer of complexity which requires estimations of the ego motion to separate background motions from object motions. So here the temporal consistency must be maintained. The depth estimates need to be smooth and coherent across the frames. The technique here in a dynamic stereo is that the spatiotemporal matches. So here it matches the points not just across a left and right images but also across the consecutive frames. So here the optical flow integration, which helps to track the moving objects and compensate for motions when estimating the depth. So here the dynamic depth maps, which generate the depth informations for every frames and video sequences, which enables the real-time 3D scenes reconstructions over the times. So these are the some of the topics we have covered as a key point. And to come up with the applications, we can talk about the autonomous vehicles where understanding the depth and the motions of the pedestrians or vehicles or even obstacles in the real times. Robotics, navigations in a dynamic environment with moving objects. Here, the augmented and the virtual reality, I can say, it is overlying 3D objects accurately in a moving scenes, which we can talk about the motion captures also a 3D reconstructions of a moving humans or objects for animations and sports analytics. To summarize this, the dynamic stereo extends stereo vision to a moving scenes, which combines spatial and the temporal information to estimate the depth reliability. So here, by integrating the techniques like optical flow and a spatial temporal matches, it enables the machines to preserve the 3D motions in the real world dynamic environment. So basically, a dynamic stereo is an extension of a traditional stereo vision which applies to a time varying scenes, while stereo visions estimates depth from the two static images. The dynamic stereo estimates depth in a sequence of images or videos, allowing us to reconstruct the 3D motions and shapes over the times. In other words, dynamic stereos helps computer perceive how objects move in a three-dimensional space. So here first we have to see about the static, that is the stereo vision. It uses two or more cameras to compute the depth by finding the correspondence between the images. Examples: measuring the distance of the stationary objects using the left and the right camera images. The dynamic stereo is that it applies the stereo matchings across multiple frames, which captures the moving objects, their 3D positions and trajectories over the times. So it combines the spatial disparity, that is a depth from a stereo, with temporal coherence, the motions across the frames. So there are some key steps in a dynamic stereo. First one is the stereo matching. For each frames, compute disparity map by finding the corresponding points between the left and the right cameras. Here the disparity d is equal to x of left minus x of right. That is depth insert is equal to fp by d, where f is a focal length, b is the baseline distance between the cameras. So here the temporal trackings, which track the 3D points over the consecutive frames using the motion estimations, that is the optical flow KLT tracking. So the depth motions fusions, we can say the combine or the combinations of the spatial depth and temporal motions to reconstruct the dynamic 3D scenes. So for the applications, like I say, as we discussed before, the autonomous vehicles to track the 3D positions of moving pedestrians, vehicles and obstacles. In robotics, we can say like a real-time 3D mapping and navigating in a dynamic environments. The augmented reality which integrate the virtual objects into a moving scenes with the correct depth. And human motions analysis which captures precise 3D trajectories for gait analysis or sport performance. The 3D video reconstructions for VR or AR or film productions maybe. The advantage here is that it provides accurate depth information in a dynamic scenes which combines the spatial and the temporal data for a better understanding of emotions. So it supports the real-time applications in robotics, autonomous driving and AR/VR. The challenges here is that it is correspondence problems finding matching points across the multiple frames and viewpoints is difficult, especially for textureless or occluded regions. So the computational complexity here is the dynamic stereo requires a processing both disparity maps and temporal motions. And the noises and lighting changes, we can say the depth estimations can be affected by shadows, reflections or low textures areas. And the key insight I can say it is dynamic stereos enables emissions not only to perceive depth but also to understand the motions of the object in a 3D, which is crucial for advanced vision tasks like autonomous navigation and human activity analysis. So these are some of the points we have covered. That is, it extends the stereo versions of moving scenes. It estimates the depths and motions simultaneously. So each frame space provides us disparity informations, which is useful in a dynamic 3D reconstructions and handle moving the object in the stereo videos. So the motion parallax exploits for depth recovery. So it requires a temporal matchings of a features which combines optical flow and stereo disparity, which helps to infer a 3D motion field. The depth discontinuities complicates estimations used in autonomous navigations, which is applicable in a surgical motions analysis. The multi-view geometry essentials, which relies on epiporal constraints where the camera calibrations is critical, can estimate the structures from a motion, that is SFM, which provides both motions and a shape cues. With the real-time dynamic stereo is challenging. So deep stereo models is improved accuracy, enables the realistic 3D scenes interpretations. So that's all about the topics we have covered in a dynamic stereos. We can move to the next topic. Motion parameter estimation. Once motion is detected in a video or an image sequence, the next step is to quantify it. The motion parameters estimations involves calculating the characteristics of a motion such as velocity, directions, accelerations, rotations and trajectory of an object. So these parameters provides a precise description of how objects moves, which is essential for applications like robotics, videos, surveillance, autonomous vehicles and human activity recognitions. So the key motion parameters is the first one is displacement. Here the delta of x comma delta of y, which measures how far an object has moved between the frames, often computed using the optical flow feature tracking like KLT or the block matching. So this is all about the displacement. And next we are going into the velocity v, where the speed and the directions of motions plays a major role, which calculates as a rate of changes of displacements over the time, which is v is equal to delta of s by delta of t, where delta s is displacement and delta t is a time between the frames. The next one is the accelerations, measures how the velocity of an object changes over the times. It is useful for detecting the sudden movements or the changes in the motion's behavior. Next one is a theta, that is directions, or we can say as orientations. So here, which indicates angle of motions related to the reference axis, can be derived from a motions vectors, that is theta is equal to arctan of v of y by v of z. The trajectory or the path is a complete path traced by an object over a time. So the importance of the predicting the future position of or analyzing the motion pattern basically. So here the rotational motions for rigid bodies, the motions may include the rotation as well as translation. The parameters like angular velocity and rotations matrices are used. So there are some of the techniques for the motion parameter estimations. We can see one by one. First one is optical flow, which estimates the motions vector for each pixels and derives the velocity and directions. The second one is a KLT tracker. It's basically a feature tracking. So it tracks a key points to compute the displacement, velocity and the trajectories. So third one is a dynamic stereo, which provides a 3D depth informations for motion estimation in 3 dimensions. Next is a Kalman filtering or the particle filtering, which predicts and smooth motion parameters over the time, especially in a noisy environment. Some of the application I can say, autonomous vehicles to estimate the speed and the trajectories of the pedestrians and other vehicles, as well as robotics for controlling the robot motions based on moving obstacles or the targets. Next one is a sports analysis, where the analyzing players movement, ball trajectories and performance matrices. In healthcare, it's monitor the gait pattern or the limb movement in our rehabilitations. As well as in surveillance, it detects the abnormal or suspicious motion in our public areas. To summarize this, we can come with the motion parameters estimations translates, which observed the motion into quantifiable data like velocity, directions, trajectory, and rotation. By extracting these parameters, computers can understand, predict, and respond to a dynamic scenes effectively, forming a critical part of motion analysis in vision-based systems. So basically, to give an overview of the motion parameter estimation, motion parameter estimations involves determining of the quantitative measures of a motion from image sequence or videos such as velocity, accelerations, trajectory and rotation of moving objects. So this allows the machines to understand not just that something is moving but how it is moving in a scene. About the conceptual understanding, the motion parameters estimations extracts motion descriptors from either a 2D image sequence, that is apparent moving in a image planes, example optical flow, or a 3D reconstructions like true motions in a world coordinates, often using the stereo or a dynamic stereo. Examples, a car in a traffic, we can estimate its speeds, that is meter per seconds, which are directions and the trajectory using the motions parameter and extracted from the camera frames. There are more key parameters. Let's talk about the translations. Here the motions along with x comma y comma z axis measures as a displacement per unit time. So the rotation here is the angular motions around an axis. Example, rotating a fan or turning the vehicles. Next one is a velocity, the rate of change of position, such v is equal to dp by dt. So the acceleration here is a rate of change of velocity, which is useful for detecting the sudden steps or stops. The fifth point here we can talk about is a trajectory. Here, the path of the object in a space over the times, and optical flow vectors with the local motions in an image plane used to compute about the parameters. There are some techniques for motion parameter estimations, that is optical flow based estimations. It used per pixel motions vector to compute the average motions or local motion statistics. The feature tracking here is track distinctive point using KLT tracker across the frames to calculate the displacement and velocity. Next one is a 3D tracking or dynamic stereo, which compute the real world 3D position over the time, which estimate the 3D motions parameters, that is a velocity, trajectory, rotations. The motion model here, it fits a mathematical model, example linear quadratic, to track the points for smoother estimations of velocity and accelerations. We have discussed about the applications here before. So now I'm moving to the advantages, which provides a quantitative measures for advanced motion understanding, can be applied in a real-time system for navigating, tracking, or even monitoring. But there are some challenges over that. I can say it's a noise in measurement. So the small error in optical flow or a feature tracking can affect the parameter estimations. So here the calculation is that it is moving objects may be blocked temporarily. So it is complex motions also comes into the pictures, like a non-linear trajectory or the rotations increase computational complexities. When we have to talk about the dynamic background, here, the moving backgrounds complicate motion estimations. The key insight I can give for this is that the motion parameters estimations allows computers to move beyond detecting the motions to understanding the dynamics of moving objects. So, which is critical for robotics, autonomous systems, and a human activity analysis. So these are the some of the topics we have seen in basically the motion parameter estimations. So the key points we have covered, the conceptual understandings we have covered over that. So and techniques as well as advantages and challenges to this. So these are topics we have covered. Next, go for the next topic. Interactions to pattern analysis. So, in the world of computer vision and data science, the raw data alone, whether images, videos, or numerical data set, often does not provide immediate understanding. The pattern analysis is a process of examining data to detect the irregularities, structures, or the trends, and to classify or group similar elements. It enables the machines to see beyond individual pixels or numbers and make sense of the underlying structures in a data. At its core, pattern analysis involves two main tasks. First one is a clustering, which is an unsupervised learning which groups similar data points together without prior labels. Example, grouping customers based on purchases, behavior, or clustering similar images. The common algorithms in a k-mean, k-medoids, hierarchical clustering. Second one is a classifications. It is a supervised learning in a machine learning technique where it assigns a new data points to predictify the categories based on learned patterns. Examples, recognizing whether an email is spam or not, or identifying the handwritten digits. Techniques, discriminant functions. decision trees, or SVM, that is a support vectors missions. The pattern analysis is crucial in many applications. First one is a face recognitions. It matches a face to a database of known identities. The medical imagings which detecting the tumor or the anomalies in the scans. Here the speech and gesture recognitions interrupting the spoken word or a body movement. The data mining identify the trend, associations, or unusual patterns in a large data set. The strength of the pattern analysis lies in its ability to extract the meaningful informations from complex or high dimensional data by detecting similarities, differences, and trends. It allows the systems to make predictions, recognize objects, and automated decision makings. To summarize this, the pattern analysis transforms the raw data into the actionable knowledge, whether through the clustering or classifications. It allows the compute to understand, interrupt, and respond intelligent to visually. So the auditory or even numerical data. So it's forming a foundations for artificial intelligence and machine learning applications. To start with the pattern analysis overview, pattern analysis is a systematic study of patterns in data to understand the structures, relationships, and underlying rules. In computer vision and motion analysis, it involves analyzing spatial and temporal features to classify or clusters object, motions, or textures. Think of it like making a sense of a patterns we detect to extract the meaningful insight from a raw or a processed data. The conceptual understanding here is a pattern recognitions with us the pattern analysis. So pattern analysis or the pattern recognition which focus on the classifying or labeling pattern for recognitions. For analysis, it focuses on exploring and understanding the structures of a pattern, often using the statistical or the computational techniques. Example, the motion trajectory of players in a football games. The pattern recognitions identify the running versus the walking. The pattern analysis understand the team formations, player interactions, and movement strategy. So these are the conceptual understanding or the difference between the pattern recognitions and pattern analysis with an examples over that. Next, we are moving to the key picture or the key technique in a pattern analysis. First, we are going to the clustering, which is an unsupervised analysis which groups similar patterns together without prior labels. Algorithms used in the unsupervised analysis is k-mean clustering and k-metods. K-means is a partitions data into k clusters by minimizing intra-cluster variance, and k-metods is similar to k-means but uses actual data points as a cluster centers. The applications here is a video segmentations which crowd analyzes anomaly detections. So in the classification, it is a supervised analysis which assigns a pattern to predefine the classes based on labeled training data. The algorithm here is a discriminant functions analysis, that is DFA, and the support vector is a SVM and the neural network. The statistical analysis use probability models to describe the patterns and relationships. Examples: Gaussian mixtures models, Bayesian inference. The dimensional interactions is a reduce the high dimensionality data to essentially features for easier analysis. So here the technique used is a PCA, principal component analysis, and LDA, linear discriminated analysis. The temporal pattern analysis is to study the motions over the time using trajectories, optical flow, or a spatio-temporal features. The applications over that is the actions recognitions, anomaly detections in surveillance and gesture analysis. We'll discuss about some of the applications of this pattern analysis. The first one is a motion analysis, which detect abnormal patterns in a human's or a vehicle motions. The video surveillance, which identify the unusual behavior or events. Even in the medical imagings, analyzes tissue textures, dynamic psychological patterns, and in sports analysis is to study the player's strategies and formations. The robotics and autonomous vehicles understand the environment pattern for navigations. There are some of the advantages, challenges also. We'll discuss on that. The advantages here is that it helps in understanding the structures and the relationships in a complex data, can detect hidden or subtle patterns not obvious from a raw data, supports both predictive and descriptive analysis in a vision systems. Some of the challenges facing here is that it is sensitive to noise, occultations, and dynamic backgrounds. The high dimensional data may require computationally intensive analysis. The choice of clusterings or classifications algorithm can strongly affect the results. Temporal patterns requires accurate motions trackings and feature extractions. Some of the key insight I can give for this is that the pattern analysis is about the interpreting and quantifying patterns in motions and visual data, providing the foundations for advanced tasks like classifications, clustering, action recognitions, and behavior understanding. The key features we have seen in this topic is that pattern is equal to the regularity in a data. Next is a pattern analyzes identities, similarities, and the structures. We have also discussed about the helps to recognize the visuals or the motion patterns, which includes a clustering and classifications task. It used in biometrics, LCAS, and computer visions, which converts the raw data into a meaningful informations. The key challenges here is the variabilities in the data and the dimensionality reductions often used. There are two machine learning techniques or the methods, that is supervised and unsupervised methods used in this. The feature extractions is crucial for accuracy. The spatial patterns to the textures, which is a temporal to the motions. So here the clustering groups similar objects and the classifies assign the labels to the patterns, and the statistical decisions theories forms as a base. It is used in speech, image, and video recognitions. The pattern analysis supports diagnostics in LCAS, which machine learning integrates the pattern techniques. The feature normalizations improves the comparability evaluated by confusion matrix and accuracy, the foundations of AI-driven visual systems. So these are the topics we have seen in these topics. Next we'll move on to the next topic.